Okay, in this video I'm going to show you how to graph quadratic functions and identify their characteristics. So the parent functions for quadratic functions is this one, y equals x squared. And why is it quadratic? Because the largest exponent is 2. Okay, that's why it's called quadratic instead of linear. If the largest exponent was 3, it'd be called a cubic. And if the largest exponent was 4, it would be called a quartic, and so on and so on. But this one is very important to memorize. Y equals x squared. So I'm going to start out and pick some x values. And the simplest x value we can pick is x equals 0. Alright, so when I substitute x equals 0 into that function, I'm going to square 0. When I square 0, 0 times 0 is 0. So my first point is going to be at the origin. Okay, that is the point 0, 0. When I plugged in 0, I got an answer of 0. Okay, 0, 0. Alright, so the next simplest number to plug in is positive 1. So I'm going to substitute positive 1. 1 squared means 1 times 1, and that's still a 1. Okay, so when I substitute a positive 1, I get a positive 1 answer. So when I plug in a 1, which is my x value, I get an answer of positive 1, which would be an answer of that be the y-axis. So where the blue one and the red one intersect, I put a point. So there is 1, 1. Okay, 1, 1. First one is x. Second value is the y. Okay. All right. I'm going to keep going. I'm going to substitute in. This time I'm going to substitute 2. So let's get that out of the way. Substitute 2. All right. That's 2 squared, which you can do in a calculator still. 2 squared. To the same thing, it means 2 times 2, and that's 4. So when I substitute 2, I get a 4. So when I substitute a 2 in there, which is 2 is right there, I get an answer of 4. 2, 3, 4. So where the red 4 and the blue 2 meet, that's my next point. Okay. Alright, and let's see. I think I have room for one more because these are going up pretty fast. Okay. Okay, let me plug in 3. Alright, 3 squared means 3 times 3, that's 9. So when my x value is 3, which is there on the x-axis, I go up to 9. 5, 6, 7, 8, 9. Okay? So where the blue 3 and the red 9 cross, that's my point there. Now, I could keep going. I could substitute 4, I could substitute 5, but I don't have enough blocks going up to actually graph those dots. So I'm not going to plug in anything larger than 3. Now, one thing you have to remember when you're substituting, we love positive numbers, but sometimes we don't like negative numbers as well for whatever reason. Think about negative numbers substitute. Now, be careful, a little more careful when you substitute negative numbers, especially if you're just putting it in a calculator. Okay, negative 1 squared, that would be, if you put it in the calculator like that, that would calculate incorrectly, because what that would do is actually multiply 1 times 1, which is 1, and then make it negative. And the answer when you plug in negative 1 is not negative 1. What you need to do if you're going to use your calculator is use parentheses on your calculator. Use a left parenthesis, negative 1 squared, right parenthesis. Okay? Alright, so literally means a negative 1 times another negative 1, and a negative times negative is a positive 1. So when I substitute in a negative 1, okay, and here's negative 1 on the x-axis, I still get a positive 1. So my point on the left side is going to be symmetric to this point. These 2 points right here are going to be symmetric, and that's what's going to happen with quadratic equations. You're going to have some symmetry, definitely going to have some symmetry. Alright, let's substitute negative 2. Okay, and again, negative 2. If I really want to do it properly, I need to put it in parentheses. which means -2 times another -2, and that's a +4. So on the x-axis -2, on the y-axis +4. Where they meet, there's another dot. Again, it's symmetric with this point over there. Those two are symmetric. And let's do one more. -3 times a -3 is a +9. Okay, so at x equals -3, I go up here to +9. Okay, this time a quadratic is going to be a curve. It's going to have a curve shape. It's not going to be a line. It's going to be a curve. So be careful. Only linear functions have a line shape. Okay, absolute value do also, but they're essentially two linear functions. So, but that's y equals x squared. Okay. All right. Let's go through the characteristics. Okay. If you watch my video on linear, it should go pretty quick. Domain is what can I substitute? What are my x values? What can I possibly plug in? What can I substitute? Let me write like this. What can I substitute? Okay, into the function. Okay, and we call that x values. Alright, so if you think about it, we substituted a +1, we substituted a +2, we substituted a +3. We could have substituted +4, we just couldn't have graphed it because we didn't have enough blocks going up to graph it. We also substituted in 0, first number. We substitute -1, we substitute -2, we substitute -3. So we could really substitute any number we could imagine into that function and get an answer. Doesn't matter what our answer is. Sometimes it was 0, sometimes it was 1, sometimes it was 4, sometimes it was 9. Okay, so on. Okay, doesn't matter. When we're talking about domain, we don't care what our answer is. We just care, do we get an answer? And that means we can substitute any number in. So that funny looking R means all real numbers. We can substitute any number we want to and get an answer. Another way to write that is like this. It's called interval notation. Negative infinity to positive infinity. Negative infinity means I can substitute any negative number in that I could think of. The side, it's like a sideways 8. The positive infinity sign means I can substitute any positive number in. Okay, and of course in between there is 0. Okay, I can substitute that also. Alright, range. Range is typically a little harder. Okay, range is the y values. Okay, so you're going to look on the y-axis. The y-axis is the one going up and down. X-axis going left to right. Okay, all right. What answers can I get? What answers are possible? All right, question mark. All right, is there any way for me to get an answer of 0? Okay, sure there is. So that right there, when I substitute x equals 0, I got a y equals 0 answer. I could have got a 0 answer. Is there any way for me to get an answer of 1? Yeah, there's 2 times I got an answer of 1. All right, when I substituted a +1 in, and when I substituted a -1 in, I also got a positive answer of +1. Okay, right here. Okay, so yeah, I could have got a 1. Alright, is there any way for me to get a +4? Yes, there is. Okay, when I substituted +2 in there, I got an answer of 4. Is that point right there? When I substituted in -2, I also got an answer of +4. So absolutely, there's a way to get an answer of 4. There's another way to answer to get a 9. And just because I'm skipping numbers between 0 and 1, and between 1 and 4 and 4 and 9, there's ways to get those answers too. There'd be irrational answers, but there's a way to get those answers. I could say, is there a way to get a 3? Yeah, sure. Here's 3 on the y-axis. I could put a point there, and I could actually find a spot down there in the x-axis where that answer, where if I plug that number in there, I would get the answer 3. And the number I'd plug in is actually square root of 3, which is an irrational number, but it is a number. It's a part of the real number system. So my range, now I could get a 0, I could get a positive 1, I could get a positive 4, I could get a positive 9. Is there any way for me to get a negative 1? It's kind of messed up here. Is there any way to get a negative 4? Alright, so let's see, 1, 2, 3. Here is a negative 4. If you look this way, or you look left and right from there, do you see any part of that red curve that goes there? No. There's no place on that U-shaped curve. Okay? This U-shaped curve. Okay? There's no place on here that gets down to negative 4 or negative 1 or negative 9 or anything below the x-axis. So we say the range, the lowest number we can possibly get, the smallest possible answer we can get is that 0. That's the smallest we can get. So we say our range is 0. Now we can get up to 9, we can get up to 16 and 25 and 49 and 121, and I mean those are all called perfect squares. And we can get up to a million or a billion. We can go as high as you want. So we say the lowest it can get is 0, and the highest it can get is positive infinity. Now, when you're writing interval notation, because this is what it is, we never put a bracket around an infinity sign. I mean, doing that would be incorrect, because we can never say a specific number for an infinity sign. You know, a very large number like a billion, I could say 1,000,000,001, which is a little bit larger than a billion. And you could come back and say 1,000,000,002, which is even larger. So we can't say a definite number for an infinity sign. We just have to understand the concept goes for as large as you could imagine. So let me get that bracket off. I always put a parenthesis around an infinity sign, always. Now, what about the 0? Do we use a parenthesis there, or do we use a bracket? Really, the correct answer is a bracket, because we actually do get a y answer of 0. It's hard to see, but right here, okay, at the origin, we get an answer of 0. So when we can actually get that answer is we have to use a bracket. Okay, so we're going to use a bracket around 0 and say, well, we can get an answer of 0. We can get anything above 0 also, like 1 or 2 or 3 or 5 or 10 or a million. So that's the range. All right. This now, if you listen to the video on linear functions, intervals increase was always just the whole thing, or it was, or it was none. Okay. When you get into higher order functions like quadratic or cubic, the larger the exponent, more curves you have, you're going to have sections that are increasing, sections that are decreasing. Okay, so if we look at this U shape and we put our little person in there, like if you're watching the linear function, I put a little person there. I start as far left as I can. Okay, all right. And this is not hard to see. From here to here, he's going down like he's going down a roller coaster. Always make him go to the right. Okay? If you actually have that little person walk on that curve, he's going down. Okay? Until he gets to the bottom of that curve. And then so this kind of brownish highlight, that's part of the curve that's going down. That part is decreasing. Okay? All right. So like a roller coaster, if you actually start, and I'll do this in, I guess it's pink, from here on up, that's increasing. Okay? So your little man starts here. Okay, he goes to the right, like always. Always go to the right. He's still decreasing when he's there. He's still decreasing when he's there. He's still decreasing when he's there. Alright, now he gets to the bottom of this little roller coaster. Oh, he's not decreasing. Now he's not increasing either. He's at that one little spot there where he stopped decreasing and he's about to increase. But he hasn't started increasing yet. Okay? So when he keeps going, he gets to here. Oh, now he's increasing. Now he's increasing. Now when he gets to here, he's still going up. Okay? So where is the interval IOI? Is abbreviation for interval of increase. Okay, going up. Okay, now always, and this is the hardest thing to get students to understand, always the x values. Okay? Alright, so where does he start? Right here is where he starts increasing. At what x is that place? Well, over here is x equal 2. Over here is x equal -3. At x equals 0, that's where he's going to start increasing. Alright? Alright, at x equal 1, is he increasing? Yep, he is. At x equal 4, is he increasing still? And he goes right, yes. At x equal, oops, I did it the wrong way. I did this thing I tell students not to do. At x equal 1, is he increasing? Yes. At x equal 2, is he increasing? Not at 4. That's the thing to fall into very easily. Don't say at 4. At x equal 2, is he increasing? Yes. Let's go to 3. Up here at this point, at that point at x equals 3, is he increasing? Yes. So at 0 and at x equal 4, he'd be increasing, so on. So as you go to the right, that means to the right forever, he increases. So always put a parenthesis around here. Now, this one does not get a bracket this time, because at that very instant where he's at 0, he's not going down, he's not going up. So this deserves a parenthesis. That means for anything just more than 0. Anytime more than 0, he's increasing. And anything to the right of this spot, he's increasing. Alright, interval of decrease. Let's talk about interval of decrease. Okay, so this brown highlight, this is the section of the curve he's decreasing. Okay, where does he start? Now again, x values. Okay, so way up here, okay, at way up here, he's starting to decrease. Again, don't go over here to the y value. Go to the x value. So at -3, he's decreasing. Alright, let's go to this dot right here. At -2, when he goes to the right from there, he's decreasing. At -1, he's still decreasing until he gets to 0. Okay? But don't make this mistake also. In fact, don't say 9 up here. This is 9 on the y-axis. Don't say he starts decreasing at 9. That's a y value. The x value is -3. Okay? Let's say -3. And he stops decreasing at 0. Okay? Definitely stops decreasing at 0. That part is right. Let's say -3 to 0. That's where he stops decreasing. Okay? But -3 is not right. Okay? Because if I had room, I could make my curve go up, and I could put my little man at x equal -4 way up here where you can't see, and he'd still be decreasing. Or at -5, or at -6. So we say he starts decreasing as far to the left as you can imagine, which we call negative infinity. And again, at 0, he's not decreasing. He's already stopped decreasing at 0. So we say just to the left of 0. That's what that parenthesis means. To the left of 0. Okay? And this means just to the right. As close to 0 as possible, as you can imagine. But definitely to the right of 0. Not exactly at 0. Alright, x-intercept, okay, it's not a hard concept. It's where does this curve cross the x-axis? It's hard to see maybe by this point, but right here, the curve gets low enough to hit the x-axis. So where in the x-axis does it touch at? At x equals 0. Alright, where does this curve cross the y-axis? Okay, well the y-axis also crosses at y equals 0. Okay, so it's on 0. It's not at 3, which is right there. No, curve's not there. It's not at -2. No, it's right there between, right in the middle. Y-intercept is 0. Okay, right end behavior. Okay, let's move this out of here because can't see it's good. Okay. Alright, so what's the right end doing? So I'll put my little person over here, and just like always, you make him go to the right. So at here, um, when he's at this dot, what's the y value? Well, it's at 4. Okay, if he goes a little further to the right, um, let's say he's up here. Now he went further to the right. Well, now that y value is 7. And he goes a little further to the right. Now I go across here. Well, now the y value is 9. So the further to the right he goes, the higher the answer is. Okay, so we write it like this: as x, I always start with x, just like the alphabet. As x approaches, that little arrow means approaches, gets close to, because we never can actually reach infinity, because infinity is not an exact number. As we go toward the right, positive infinity. If we went to the left, we say negative infinity. We say the answers are getting larger and larger. That's also getting to be a large number, positive number. Okay? Alright. Now when we're doing left end behavior, this is the only time you make your little guy go left. So imagine my little person on the left side. And this time he's going left. Don't do that for interval increase or decrease, only for left end behavior. Alright, okay, so here's an answer. I go over to the y-axis. That answer was 3. Alright, I go a little higher. Okay, go over to that y-axis. This answer is 5. Okay, so I go up here to, let's go way up here to where you see that point. Go over to the y-axis. That answer is 9. Alright, so as this time, it's kind of doing the same thing, but this time you got your little guy going to the left. So we say negative infinity when you're going toward the left. Okay? Positive infinity means you're going to the right. Alright, so what happens as you're going left? Well, the y values, the answers, also still get bigger and bigger, just like on the right side. Okay, when you went right, the curve went up. When you went left, the curve went up also. Okay, so try to understand. I mean, you can understand this. You got an infinity sign here and here, but they stand for different things. This first infinity right here means we're going right. The second infinity means we're going up. Okay, as we go to the right, we're going up. All right, now what's a negative infinity mean? Well, it can mean going left, and if we had a negative infinity over here, it means going down. But this one is same as the one on the right end. That one means going up also. So if you have a negative infinity, down. Okay? Alright. Alright. The next graph we're going to do is this one. And sometimes students will kind of shut down and say, "Oh my gosh, how do I do this problem?" And maybe they're going to attempt to do some algebra here and say, well, x plus 1 squared, and hopefully we don't do that. X plus 1 squared equals this. Oh my goodness, no, don't do that. X times x, 1 times 1. Oh, don't do that. That's terrible. No. Alright, it means this. It means x plus 1 times another x plus 1. And when you use FOIL on it, you do x times x, which is x squared. You do x times 1, which is a positive x. And you do this 1 right there times that x, which is another positive x. And finally you do last, 1 times that 1, which you get a 1, and when you combine these two, the whole thing, you get x squared plus 2x plus 1. Alright, and still if you do all that, you're going to be stuck, because what on earth does the graph look like? Okay, so that's all good to simplify. It might be called simplify every now and then, but no, for graphing, this is what I want you to do. Okay, I want you to think of this. Uh, the parent function, and how are these two alike? How are these different? Well, of course, they're both quadratic. Biggest exponent's 2. Okay, so what happened is they actually put a little plus 1. They grouped that x and made a plus 1 behind it. All right, this is going to require a shift. Okay, that plus 1 means we're going to shift y equals x squared left 1. Alright, everybody can see why it's 1, because it's a 1. If that's at a 2, you shift left 2. Alright, but it's left because when you see a plus sign there, it's left. If you saw a minus sign there, it'd be right. So what I really would like you to know how to do, and you can do this, not hard, is to imagine or graph y equals x squared, which was the last problem. Y equals x squared, okay. Here's a point at the origin, then you go right 1, up 1. Alright, go back to the origin, go right 2, up 4. Okay, go back to the origin, go right 3, go up 9. Okay, here are the points. 0, 0, 1, 1, 2, 4, 3, 9. And then it's symmetric. So you just go across the x-axis, say y-axis, and go and say there's a dot right there. Those two are symmetric, and then this point here, go left 2 and up 4, you go left 3 and up 9, okay, and draw your curve. Okay, is this going to take us way too much time to be doing an X or a T chart or whatever, and then trying to think of numbers to plug in there? Because especially when it's shifted left or right, you're going to have a hard time picking the correct x values. You're going to pick x values, and you can plug them in correctly and get part of the answer, but you might not be able to see the U shape, which all these should have, unless you pick correctly, and you might be frustrated. Okay, no, let's do an easy way. Okay, let's take this graph and shift it left 1. Okay, so instead of a point here at 0, 0, no, let's put it right here at negative 1, 0. Alright, instead of 1, 1 right there, let's put our point at 0, 1. Instead of at 2, 4, which I had a second ago, let's shift it 1 left, say 1, 4. Okay, instead of 3, 3, 9, which is up here, let's say 2, 9. Go to the right 2. Everything's shifted 1 left. Okay, now once you got one side done and you know where your vertex is, this is very important, you know where your vertex is. Okay, your vertex. Then it's always symmetric around the vertex. Okay, alright, so we can put a point over here that matches this one. We can put a point over here that reflects across this one. Okay, we can put a point right here. Just be careful. Okay, and sometimes I draw like a squiggly line right to where I know it's gonna flip over. This is a reflection across that green line. Okay, so here's your graph. Okay, that green graph. Okay, what's the domain? Again, almost all functions have a domain of all real numbers, and it's not that you need to get lazy, just automatically put things all real numbers there for domain all the time. because then sometimes students didn't have it that. I just put the range, the same thing. And range a lot of times it's not all real numbers. Only time function you need to watch out for, okay, these are rational functions. The domain is not all real numbers there. Square root of x, that's not all real numbers because we can't substitute negative numbers. Natural log or any logarithm function, you can't put in negative numbers there either. So pretty much beside that, you can use all real numbers, but think about it. What can we substitute? We can substitute 0. We got an answer. Okay, we get an answer. Definitely get an answer. An answer of 1 when we substitute 0. When we substitute 1, got an answer of 1, 2, 3, 4. Got an answer of 4. When we substituted 2, we got an answer of 9. We substituted -2, got an answer of 1. Okay, and we can imagine we can substitute any. What can we substitute? What can we substitute into for x? We can pick any number. We can pick 1,000,000. Okay, it'd be a huge number. 1,000,000 has 1 with 6 zeros behind it. We could add 1 to it, which make that 1,000,001, and we square it and we get an answer. It'd be a huge answer. We don't want to, certainly can't have a chance to graph that answer. We get an answer. That's all domain is what numbers can we substitute in and get some kind of answer, which is, again, everything, any number we can imagine. All real numbers, well, I can write like this. Don't have to write it both ways, just know both ways. The range, okay, ranges are answers. These are y values. Y values. Okay, y values for range. Okay, all right, well, we got these 2 points here. We're at a height of 1. That's all y value is how far above the x-axis it is. These y values are 4. Okay, 1, 2, 3, 4. We got dots at 4. We got dots at 9. We got dots in between 1 and 4. I mean, a curve is infinitely amount of dots. We just don't show all of them because they're infinite amount. Okay, so the range is definitely at 0, and we can go up forever. Okay, always put a parenthesis around an infinite sign, either positive or negative. All right, what about 0? Can we actually get an answer of 0? Absolutely, it's right here. So we use a bracket, not a parenthesis. Okay, now we can't get anything below 0. We don't have any dots down here below the x-axis anywhere. No. So sometimes I see just students kind of not mindlessly just putting down all the numbers, because we do it over and over and over. They're not thinking out. They're just kind of going through things. All right, interval of increase, okay, is pretty much like the last example, first example, but this graph is shifted over. So at what x values, I got to tell myself many times also, at what x values. So look on the x-axis, go look at your graph, but go down or up to your x-axis. At what x values is the graph going up? Okay, all right, if I put my little guy right here, not putting him way back to the left, because from here on over, he's going up. He's climbing a hill. He's riding up a roller coaster, walking up a hill, whatever you want to say. All right, go to your x-axis. X-axis here is at -1. The x value of this point is 0. X value of this point is 1. X value of this point is 2. So it starts at -1. That's where he starts going up, and he goes on forever. Okay, just like the last problem, at that particular spot right there, you're going to definitely see that in calculus when you take the derivative of that function, and you find that the slope of the tangent line there is 0. That means at that one particular instant that graph is not increasing or decreasing. So we have to use a parenthesis, very important, not a bracket. Okay, interval of decrease. Start your little man as far left as you can, all this area right here. all this. This whole section of the graph is decreasing. Okay, where does he start at? Well, definitely don't go over to the y value. Absolutely don't do that. All right, go down to the x value. 1, 2, 3, 4. But don't say -4, because that's not where he truly can start. Visually, that's where it looks like x equals start. But if we had a bigger grid, we could say, well, we could put him at -5 and he'd be decreasing from there on to the right. At -6. At negative infinity. So you have to use your imagination. Alright, until you get to -1. Don't automatically put 0. And again, just before, just to the left. Just to the left of -1. This -1 up here means just to the right. Okay. X-intercept. Where's this green curve across the x-axis? Alright. It's right there at x equal -1. What's the y-intercept? Okay. It's over here. Alright, that's at +1 on the y-axis. What's the right-hand behavior? Just like the last example, he's going right, we get an answer of 1. When he keeps going, we get an answer of 4. Keep going to the right, you get an answer of 9. So the farther you go to the right, the bigger the answer gets. So as x approaches positive infinity, y also, as the x values get bigger, the y values get bigger. X value here is 0, the x value here is 1, x value is 2, x value here is, you get 3, x values are getting bigger, and y values are getting bigger. Alright, left hand, you can get your little guy. You don't have to draw it, just visualize it, make him go left. Only time you make him go left. Okay, so right here the x value is -2, y value is +1. At x value of -2, the y value is a +4, positive, and the x value is a negative. Let's see, 1, 2, 3. That was 3. At -4, the y value is a +9. So as the x values get smaller, that's what negative infinity means. Okay, -1, -2, -2 is smaller than -1, -5 is smaller than -4. Okay, y is still doing the same thing. And that's what's going to happen with quadratic. These will be the same. Either both be positive infinity or both be negative infinity. Okay? Alright, let's try another one. Okay, this function. Okay, really want you to contrast this with this function. And if you remember, this was shift left 1. Okay? Because the 1 is grouped in with those parentheses with the x. It's kind of locked in like with the x, like two people in the same room. Okay? The parentheses are like walls that keep the x and the 1 together. When that happens, that's a left or right shift. Okay, if it said x equal y equal x minus 1 squared, that would be a shift right of 1. Okay, well this one's a little different. There's a +1 behind it. See, it's like in a different room. When that happens, that's a shift up, not right, and you have to know which way you're shifting. And the good thing is, when we do any kind of function, if rational or cubic or quartic, when we have a number grouped in with the x, it's always going to be a shift of left or right. When the extra number is not grouped in with the x, there's no square, there's no parentheses, or there's no division line or anything like that, it's going to be shifted up or down. Alright, so just really briefly,